So here's where we got to last time. We learned that in an atom bonded to a spring, which we're calling a microscopic oscillator, the values of k plus u that are possible are discrete. And in fact, they're separated by an amount of energy delta E, which is constant, so the separation is always constant. And that's equal to this constant h bar times omega, where omega is the angular frequency of the oscillator, and it has the value that we worked out from a differential equation back in end of chapter 4. In this case, though, the spring stiffness is the stiffness of the interatomic bond modeled as a spring, and the mass is the mass of one atom. So it's not the mass of a kilogram of atoms. I'm talking about one oscillator here. And we call that one quantum of energy. It has some value in joules, and we'll spend some time calculating that this afternoon. And that's the value of the constant h bar. We also saw that we could figure out the number of ways if we had a certain number of atoms. So in the Einstein model of a solid, we are modeling each atom as if it were three independent balls and springs, one oscillating in X, one oscillating in Y, and one oscillating in Z, that aren't coupled to each other, which is a simplification, but it actually works fairly well. And so we could actually say if we have this much energy, which is, we would have to divide into these quanta that match the energy level differences. So if we have this much energy, this many quanta of energy, how many ways could we arrange that energy among all the oscillators in our particle of matter, which would, and we found that we could count on our fingers when there weren't very many oscillators or quanta, but that wasn't practical when there got to be more. So we have a combinatorial formula for this. So the number of ways of arranging q quanta of energy, so q of these little packets, h bar, omega 0, among n oscillators was given by the equation q plus n minus 1 factorial over q factorial times n minus 1 factorial. And each of these arrangements is called a microstate. And there are lots of different microstates for one macrostate. A macrostate is just the total amount of energy you've got and the number of oscillators you've got, the size of the particle. And we saw that that using this, we could calculate so we wrote a little program, which I've decorated with some titles here, to calculate, oops, that's not the one I want, this one. To just calculate and plot for a system that involves two objects, not necessarily the same size, that are in contact with each other so they can exchange energy. The number of ways of arranging energy, so the number of microstates for every macrostate. So this axis is basically macrostates. It's the amount of energy in block 1. And in this case, block 1 has 450 oscillators, and block 2 has 250 oscillators, so it's smaller. So we have the amount of energy in block 1, so that's a macrostate. For each of this, we could calculate the number of possible microstates. And we found that the most probable situation is the one that has the most microstates associated with it. Why is it the most probable? Well, if we just energy is bouncing around in this system, and if we just took a photo of the system and which showed us where all the energy was once a second for the lifetime of the universe or for a long time, we'd find that the 63 or something % of the energy in block 1 and the rest of the energy in block 2. And so that's the most probable thing, because that's the thing we just see most often, although some situations that are not quite that are also fairly probable. But the probability of having most of the energy in block 1 is actually extremely small. And so questions about this piece? No. Okay. And we also saw that if we just took a logarithm of that, then if we plot the log of omega 1, which is the number of possible microstates for block 1 versus the energy in block 1, and here's the log of omega 2 versus the amount of energy in block 1, and then we take the log of omega 1, the log of the product, which is the total number of ways of arranging things. We find that there's a maximum, and it's in exactly the same place, which isn't surprising because it's the same system. But this is just a different mathematical representation. It does, by taking logs, we get to actually see what the numbers are here, where it was really way too small on that previous plot. And also, it turns out that by taking a log of omega and multiplying by this constant, which is called the Boltzmann constant, we actually are able to calculate the entropy of the system, and it's consistent with that thing entropy that physicists invented 100 years before without knowing about atoms and microstates and quantized energy, just looking at macroscopic properties to make thermodynamics work. So it turns out at the microscopic level, that's what the meaning of entropy is. It's just related to the number of ways, possible ways of arranging things. And you could think of it as the more ways of arranging energy there are, the more randomly the energy is distributed. So it's kind of a measurement of how randomly energy is distributed in a system. And I think we briefly mentioned that this leads us to the fundamental assumption in all of this, the fundamental assumption of statistical mechanics, is that for a given macrostate, so a given amount of energy and a given size of an object, every possible arrangement of energy, so every microstate, is equally probable. So maybe we should put that up here too. So we call that the fundamental assumption of statistical mechanics. And since we see from these graphs that the most probable situation is one where this quantity entropy is at a maximum, that actually leads us to the second law of thermodynamics, which can be stated lots and lots and lots of different ways. But one way of stating it is that if a closed system, meaning a system that's isolated from its surroundings so it can't exchange, can't have energy inputs from the surroundings. So if a closed system is not at equilibrium, the most probable thing that will happen is that the entropy of the system will increase until it gets to equilibrium. So a closed system will in a closed if not at equilibrium, entropy will increase. Law of thermodynamics. It's just the energy principle. So we've been working with that for a long time. Okay, so the question is, what good is this? What can we do with this? So our goal today is to start with this idea of entropy and try to get a very concrete formal definition of temperature. And when we've got that, see if we can figure out how the specific heat, the heat capacity of an object, which we worked with in chapter 7, is related to entropy and temperature. So that's the plan for today. This afternoon in recitation, what we're going to do is apply all that and actually do calculations, go through calculating everything. It's really instructive to do that, actually. It's an important thing. So we have these two blocks that are in thermal contact with each other. They exchange energy randomly. And the most probable situation is the situation where there are the most accessible microstates, or where equivalently the entropy is at a maximum, right? So I don't know how well I can reproduce this graph, but we'll try here. So this is Q1, this is entropy. This is and this is okay, and so we have at about 63% or something here, we have maximum entropy. This is the entropy. So this red graph is the entropy of block 1. Number of ways of arranging the amount of energy that's in block 1 in the available oscillators. It's 0, or it's 1 when there's no energy in block 1, because there's only one way of arranging 0 energy in lots of oscillators. And this is the entropy of block 2. And this is the total entropy, which is S1 plus S2. Because remember, we said the total number of ways of arranging energy among both blocks was equal to the product of the ways of arranging energy in block 1 times the range of energy in block 2. So S is Boltzmann constant times the natural log of omega total, which is equal to, remember so we add logs here. Okay, so this is the sum. And so at some point we have a maximum in the entropy and that's the most probable situation. And of course the slope of the entropy versus energy curve at that point is 0 because it's a max. Now, what is it that's the same for these two blocks when they are at equilibrium? So we did problems in chapter 2. We put two blocks, different sizes, different heat capacities, different initial temperatures. We put them together. We figured out what was going to happen. And what ended up being the same between the two blocks? Was it the amount of energy inside the blocks, the internal energy? Now, what was the same in the two blocks? The temperature. The temperature. So it must be the case that at this most probable situation, the temperature of block 1 has to equal the temperature of block 2. Okay, so let's run with this a little bit. Since this is a since entropy is a maximum at this particular division of energy, so the total entropy, so we know that the rate of change of entropy with respect to the amount of energy in Q1, which is how we're, Q1, which is the amount of energy in block 1, has to equal 0, because that's the slope of that curve at that point, right? But this is equal to the rate of change of the sum of S1 plus S2. And so we get ds1 dq1 plus ds2 dq1 has to equal 0. So the rate of change of the entropy of block 1 plus, with respect to Q1, the number of quanta in block 1, plus the rate of change of entropy of block 2 with respect to that same thing has to be 0. But for S2, since Q1 runs that way, Q2 starts at 0 and runs that way. So we could say that ds2 dq1 is equal to minus the derivative of S2 with respect to Q2. So a negative slope here turns into a positive slope if you're going the other way. And so we find that at equilibrium, we have the rate of change of the entropy of block 1 with respect to the amount of energy in block 1 minus the rate of change of the entropy of block 2 with respect to Q2, the amount of energy in block 2, has to be 0. And that suggests that ds1 dq1 is equal to dq2. So basically we're talking about slopes here. We're saying that at this point, this is and this slope, or the negative of this slope, this slope is minus. So we're saying that if we express these slopes as both positive, they have to be equal. Well, that's suggestive because at equilibrium, the temperature of the two blocks is equal. And so the fact that these two derivatives, the slopes of these two lines, are equal suggests that this has something to do with temperature. Now, it could be the temperature, though, or it could be 1 over the temperature. We're not sure here. So let's think about, for a minute, about what it's going to be. So the question is, are these derivatives equal to the temperature, or are they equal to 1 over the temperature? And the way to think about this is kind of to think about the slope at the beginning here. So here we have a big slope, and this is for block 1, which has almost no energy in it. So it's kind of cold, it's accepting energy. Whereas this slope for block 2 is a little bit smaller. So what do we think? Does a big dsDE mean high temperature, or does it mean low temperature? Think about it for a second. Okay, so what do you think? Okay, so most people who are willing to vote are saying 2. And that's 2 is correct, because here we've got, let's look at block 1. Here we've got a big dsDE, and yet block 1 has very little energy in it. So it's accepting energy and getting warmer. So a big dsDE means low temperature. A smaller dsDE means higher temperature. So in fact, where we get to here is that this is actually the definition of temperature. So 1 over the temperature, this is temperature in Kelvin. is equal to the rate of change of entropy with respect to energy. When you put more quanta of energy into a block, does the entropy increase fast or not fast? Now, in fact, this is a slight oversimplification. It really should be the partial derivative of S with respect to E at constant volume. What's a partial derivative? Well, if something's a function of more than one variable, so if something's S is a function of energy and volume and pressure and whatever else, you can differentiate with respect to one of these variables as long as you hold the other variables constant. So that's what we're talking about. But for our purposes, this is good enough. Okay, so this actually gives us things we can calculate. So if we say that 1 over temperature is equal approximately to the change in entropy with the change of internal energy. In a situation where we're talking about solids and there's no work done, this is going to be equal to delta S over Q. Then we could say, we can just rearrange this and say the change of entropy of a system could be calculated by Q over T. So let's see if we can just do a simple calculation for some system here. So we have some system of some size, thermal energy, 5,000 joules of thermal energy gets transferred into it, and the entropy of the system increases by 50 joules per Kelvin. What's the temperature of the system? Okay, so what's the answer? Yes, 2 is correct. It's 100 Kelvin. Okay, so we can actually calculate things. Now there's some processes that actually occur at constant temperature. For example, freezing or melting actually occurs at constant temperature. So if you plot temperature versus time for a system on some axis or other, this is time, this is temperature. A system that is in a solid state and you want to melt it and make it liquid, the temperature goes up for a while and then it reaches this melting point And it actually stays there for a while, so this is the melting point. And then once it's melted, it goes up again. So the process of melting itself, or the reverse, the process of freezing itself, actually occurs at a constant temperature. And you may have done this experiment in a chem lab at some point. Yes? Yes, you have. Okay, so you've seen that. So we can talk about melting to think about a question. In these processes, we've been talking about entropy increasing. And the second law, which didn't fit up there, says that for an isolated system, the most probable thing that'll happen is that the entropy of the system will increase. Can entropy ever decrease? For what system? Okay, so let's think of the following situation. We're going to melt some ice. So we have a gram of ice. The ice is at 273 Kelvin, which of course is a melting point, and it's sitting on a hot metal surface, which is at 293 Kelvin, okay, room temperature. And it turns out that it takes 1 gram of ice needs 335, I think, joules to melt. And the temperature is constant at 273 Kelvin while it's doing this. So let's calculate the change in entropy of the ice, the change in entropy of its surroundings, and the change in the entropy of the universe, meaning the ice plus its surroundings. So the change in entropy of the ice is equal to, how are we going to calculate that? We lost our definition of temperature. So it looks like the energy input divided by the temperature. And that comes out to a slightly positive number, which is plus 1.23 joules per Kelvin. The change in entropy of the surroundings, the metal, well, it lost 335 joules, so it's a minus 335 joules at 293 Kelvin. So the entropy of the surroundings actually went down a little bit, and it comes out to a minus 1.14 joules per Kelvin. So the change in entropy of the universe is equal to the change in entropy of the ice plus the change in entropy of the block, and we actually get a positive number, a small but positive number. It's plus 0.09 joules per Kelvin. So you're right, the entropy of one object did go down, but the entropy of the other object went up enough that the entropy of the universe actually increased in this process. What happens if you freeze water? Is it going to work the other way? Well, let's see. Suppose we have a block at 253 Kelvin, and we put a 1 gram of water at 273 Kelvin here, and it freezes. So the change in entropy of the water, we already calculated that. It's just now it's going to be a minus 1.23 joules per Kelvin because it loses 335 joules. So the entropy of the water now goes down. The entropy of the surface is, it gains 335 joules, but it's at 253 Kelvin. And so that comes out to a plus 1.32 joules per Kelvin. And so the total change, system plus surroundings, turns out to be a plus 0.09 joules per Kelvin. So no matter which way you're going, the entropy of the universe seems to be increasing, even though for things within your system, entropy can go down for one thing and up for another. Okay. Questions about this? We need more room on this board. Is the entropy of the universe always increasing? Well, the second law said that for an isolated system, the universe is certainly an isolated system. If it's not at equilibrium, the most probable thing that will happen is that the entropy of the system will increase. So, will the entropy of the universe ever go down? No. But the best it could do is break even, right? It could just stay the same if it was at equilibrium. But lots of agents like us are running around busily increasing the entropy of the universe, so yeah.
I guess I'm kind of confused. So when the entropy is always increasing, in that example that we just did right there, where is randomness going, I guess? I mean, where is it coming from?
So where is the randomness coming from? Well, in one sense, so what kind of randomness increased? In the case here, where the entropy of the surface increases, it's exactly that randomness we've just been talking about. We put a little more energy into the block, and so there's lots more ways to arrange that energy. The energy is this energy that was sort of confined in the water is now free to move around a much larger array of oscillators and places to put it. So the energy has been randomized more than it was. In the case of the water, the block of ice melting, in fact, we do end up with more ways to arrange energy, but I think a piece of that ice melting is also a positional component of entropy. Remember, we saw on Tuesday that we were talking of a gas, and the gas spreading out through the volume was randomizing position. It's sort of randomizing energy too, in the sense that if you consider a particle carrying energy, it's now over there instead of here. And I think that's a part of what's going on so there's more than one contribution to entropy part of it's arranging energy and part of it's and we're focusing on the randomizing energy part because it ties in so nicely to everything we've done this semester with the ball spring model of solids and heat capacity and things like that. And it gives us a very concrete way of calculating, a really easy way of calculating. So the last thing I want to talk about, so that we can actually do some calculations this afternoon, is heat capacity. And we saw that the change of internal energy of something was equal to the heat capacity times the change in its temperature modulo some number here. If the heat capacity was if it's in a per unit mass, then you would have to multiply by mass. But you could also express heat capacity in terms of a heat capacity per atom. So instead of per gram, it could be per atom. And so per atom, we can write the change of internal energy is equal to the heat capacity times the change in temperature, which would mean that the heat capacity of something is just the ratio of change in internal energy to change in temperature. So this is actually something we could predict. And the chain kind of goes like this. If we know for some substance we know, like copper or aluminum or something, if we know the mass of an atom and we've determined the interatomic spring stiffness by measuring Young's modulus, then we know the energy of one quantum. If we know how many particles we've got in a nanoparticle, we can figure out the entropy of the system with a certain amount of energy. If we put in more energy, we can figure out the entropy again, and then that gives us a way of getting dsDE, which gives the temperature. Well, if we did this for another set of values of energy and entropy, we could get another temperature. So then we get two values of temperature for different amounts of energy input, so we could actually calculate what the heat capacity of the substance ought to be. And the really interesting thing about this, which we'll, I hope, see this afternoon, is that it's not a constant. So people thought for a long time, until around 1911, that heat capacity was just a constant. But when scientists invented a way of getting things really, really, really cold, so to be able to liquefy nitrogen or liquefy helium and cool things down to increasingly close to 0 Kelvin, they discovered that the heat capacity of a substance actually was really different at low temperatures. And in fact, and they didn't have an explanation for this. So as a function of temperature, the heat capacity looked something like this. And that was really unexpected. And in fact, it took this theoretical framework, which we will apply this afternoon, to actually help us understand and predict what's going on. Yes?
Is T, like, as it's getting warmer, or as it's getting colder?
So this is 0, which we can't get to. So T increases this way. So at low temperatures, the heat capacity of aluminum or copper or lead or whatever you like is actually much lower than it is at room temperature. Now it kind of levels out, and interestingly enough, the value to which it levels out, which is also theoretically predictable, is it's approximately 3 times the Boltzmann constant on a per atom basis, regardless of the material, which is also kind of interesting. And I think we don't have time to do the theory on that, but if you want to read farther in chapter 12, I can see what's going on there. So what we're going to do this afternoon is start from the beginning with a substance like aluminum and a concrete sized nanoparticle. And for different values so we're going to do what's a parallel computation. So every group of people will have a different set of quanta of energy, and we'll go through this whole calculation. We're going to calculate a quantum, we're going to calculate entropy, we're going to calculate a change in entropy, we're going to calculate temperature, change in temperature, specific heat capacity. And ideally, we'll actually get a curve that'll let us see how heat capacity changes with temperature. And we'll do one together just so we can. Now, so questions about this. And it's not going to feel concrete until you do the calculation. And once you do the calculation, it will feel very concrete. And there's a lot of, when you're doing the calculation, there's a lot of asking yourself, wait, I thought I understood this, but what does this number mean? And what does that number mean? Okay, and that's why we're going to do it, because we need to do that. So given that it still seems pretty abstract, are there questions about it at this point? Okay.